performance assessment, right?
Right.
Is one that, are you finished with the sign-in sheet? Yeah, you can pass that forward, thank you. We mentioned beforehand that there are a couple of different metrics that we utilize, thank you, to characterize the overall operability of a performance or of a classifier with respect to class inclusion output. All right, so this is a simple binary classifier because we're stuck in just positive and negative. So imagine in this particular state we have actual, right? We have predicted. This is fairly easy to interpret. However, I want you guys to pay attention because I switched to the next slide. Actual and predicted are inverted. It does not matter which axis actual is put on. It doesn't matter which axis predicted is put on. Do you take that?
No.
Okay.
Sorry. Thought I had it muted.
That's all right. So, well, sometimes people need to take calls, and you get that. Actual is the label that was assigned to this particular data value within the database that has been provided to us. Predicted is often, the term that is utilized with it is often called inference. If you've ever heard the idea of to infer something. An inference is a type of predictive ideal, right? So we take into consideration previous information, we infer something based upon that. We say that predicted outputs are the labels assigned to the samples by the model. So initially, the labels assigned to the samples by the data collector, data set constructor, right? Some arbitrary mechanism of assignment for class inclusion is going to be placed within the data set. Actual is essentially akin to F, whereas predicted is akin to F hat, right? We say Y or Y hat, right? So Y, true Y underlying characteristics is considered actual. We often will assign and say that actual is related to some sort of truth statement, but it is not ground truth. Now I'll explain the reason why. There can still be error within this, all right? A sample can actually be assigned to the wrong class. That is a situation that's it's a fairly advanced problem, but the reason why I say it's a fairly advanced problem is because if a human is labeling something, you guys have all done this, and I'll tell you what you've done that you don't know that you've made a labeling assignment mistake. Now, if any of you have figured out ever how to run one of those image caches, and you do them all perfectly every time, then kudos to you, you're an amazing person. Right? I miss a bicycle every now and again. It happens. All right? That's what I'm talking about. What happens if a sample that has bicycle in it goes into, or has bicycle in it, goes into the negative class, goes into the no bicycle camp? Now you have a bicycle present, right? But the label, the information that's being provided to you from a training standpoint says there's no bicycle there. So how about confusing the model? Model goes, wheels, frame, handles. How is this a no bicycle, right? What? Right? So then it's going to output what? What's going to output?
False.
It's going to output that it's positive. It's going to say, hey, it's positive. The system's going to say it's what? It's a false positive, right? But in truth, it should have been a true positive because of the fact that the system should have recognized it. However, like I said, we're talking about it from the perspective of this is the high level stuff, but I'm gonna go back. We're gonna look at this as a baseline. We're gonna say again that we know how this works. All right, we have a rough understanding how this works. It's a 0 or a 1 on the ledger, on the key, right? And then you provide your version of the solution, and I'm checking your version of the key. However, typically what do? We just say true positive. We're saying how many that were correct, right, did you get correct? Right? How many ones did you classify as ones? So we're going to say this is a label of ones, this is the label of ones, and we'll say that when they converge, this is 1, 1, right? What happens in this case? 0, 0, right? What happens over here?
0,
0, 1. and then light down
One,
here,
zero.
1, 0, okay? It's really not difficult when you come into binary. It's not hard to overall calculate. And from a certain perspective, you can look at it and say, the accuracy of the system could effectively be drawn or written as the summation of the true positive and true negative score relative to the net number of samples within the system, right? The number you got correct out of the total of the system is a good enough metric for accuracy, right? How accurate you were, how correct you were overall. Well, I'll give you an example here in a minute. We're going to go back to the example I think I used earlier on in the system. Note, we have a lot more metrics all of a sudden. Now, this is the one that you'll see if you look at Wikipedia, okay? This is like the standard version of this. I don't know why, like Wikipedia is like the best place to find this particular graphic, but I think it's because the author of this original graphic kind of put it up there for free use, but you'll find this all over the place, like reference in publications, other websites, etc. This is kind of the population accepted version. So we notice a couple of things here. Condition is at the top, all right? What does condition stand for in this case? It says determined by gold standard, all right? Gold standard means it's determined by an expert at labeling this particular class type. Now, we say expert as someone who is notably informed on the topic, and that can even be another model, right? You can have a model that labels samples. We'll get into that potentially later on. But at the moment, that is a person, right? That is a person, or that is a group of people who are going to look at the samples and they're going to apply or provide a label for them. When I say condition or gold standard, I'm talking about that valuation. Test outcome over here is the binarized incident case for that predictive outcome. This is the inference of the model. So original condition, right? And then outcome condition. We noticed true positive in the upper left-hand corner there, right? And then true negative in the lower right-hand corner. Whereas previously, the matrix is reversed, right? Tn is in the top and Tp on the bottom, right? We flipped them. It's the only difference. This can happen anywhere, all right? I know I've noted it in a lot of different mechanisms, but the reason why they did it for this one is because it works better whenever you're putting out stuff across the axes and projecting down. It makes the process of the way in which these are oriented better for reflection, right? So it's reflecting internals of the system. So let's look at a couple of different metrics we're working with. We call false positive error. What is false positive again? That's saying it is not a case positive, but I said it was, right? So I guessed it was positive and it was actually negative. That is called type 1 error, all right? Type 1 error. Now, the reason why we say type 1 and type 2 are just because of the fact that we actually have other types of error, but from a notational standpoint, we're only going to use 1 and 2 to refer to false positive and false negative respectively. Tn and Tp, true positive, true negative scores are just referred to by their nominals, by their names. And we have one characteristic here that I want to put out as well to be able to talk about a scenario where this matters, right? Why does this matter? This matters because we have a certain, I guess you say, a certain problem we have to deal with overall. You guys remember my airplane story, right? The humanitarian airplane story, right? You got the two containers with the apples and the grenades, right? They fall over, you pick them up, put them back in their containers. How would that apply in this case? How do we apply this? What is a false positive and what is a false negative, right? Let's say that we assign the apples as negative, right? They're non-explosive, right? So a true negative would be an apple picked up off the floor, put it into the apple bin. What's going to be a false positive?
You
you thought it was a grenade, but it's actually not.
Okay, we said positive is explosive, right? Yeah. So it says, I thought it was a grenade, but it's actually an apple. Very correct. Okay. So I thought it was
False
a grenade,
positive.
but it's actually an apple. So where did I put it? I put it in the grenade bin. Okay. That's where the soldier, instead of getting the, device they need, their explosive, they just get a tasty treat. All right. They get to eat their apple and go about their business. So probably not going to be that upset, really, right? Because it's not a really defensive weapon, right? I've thought about that a lot. Grenades, not exactly something you use for like close quarter combat self-defense. It's very much an offensive weapon, So what they just happen to, the worst case, absolute worst case scenario is they provide aid to the enemy, right? The reason why is because they throw the apple thinking it's a grenade, the enemy finds it and they go, oh, it's an apple, and they eat it, and you're like, man.
Peace offering.
You're exactly. Just see apples just coming over the edges, But it can happen. You never know. What is the cost of misclassifying an apple as a grenade?
That the grenade
No,
gets placed.
no. All right. What about the other direction? Misfiling your grenade as an apple.
You could blow people up.
Exactly. That's problematic. So look here at these two scores, right? So we say that we falsely identified it as an explosive, right? Whereas we falsely said it wasn't an explosive. Look at this ratio here, that characteristic. Think about that. I could provide you with just the accuracy of my classifier that took into consideration just true positive and true negative score, right? The ones I put in the correct barrels. But what is actually the most problematic here? The most problematic is off-axis from the correct classifications. This is the reason why I said earlier that accuracy as a pure metric is super deceptive. It doesn't actually tell you how well the model does at detecting these other two types of errors. And some of those two types of errors, either false positive or false negatives, can have more drastic consequences than having a good false positive, good true negative, true positive score, right? If you're shifting into the false positive camp, what does that mean about your system? False positives, meaning there's more false positives than false negatives.
It's not working.
Well,
It's
in
misclassifying.
this particular case, if I had to make a choice between false positives and false negatives, which would I prefer?
False positive.
I want to do false positives, right? I want to be sensitive on the side of error. So I actually would want to know what its type 2 score relative to type 1 score error was, the ratio of provision there, right? So let's look down here at a couple of metrics. We have miss rate, right, which is the false negative rate of the system, which is false negative over condition positive characteristics. That's one mechanism we can look at and see how many times we falsely determine something negative versus all of the relative positives of the system. But we can also look over here at these two scores. These two scores are used frequently together to characterize some aspects of the system. First, we talk about sensitivity, which is also often called recall, and or total positive rate, right? Total positive rate score. And that takes into consideration true positives over conditioned positives, right? It's going to take into consideration things along the first horizontal axis in this case. Specificity is going to be the alternative consideration, true negative over conditioned negative, right? So it's going to be along this axis. So miss rate is along this axis. Specificity is along this axis. Sensitivity is along this axis. And false positive to conditioned negative rate is along this axis, right? Or often called fallout. Fallout is called that because of the fact that it is typically nuclear if you have a bad positive case, right? It goes nuclear, it's the fallout, right? That is a condition in which we say how many total false negatives do we have, right, within the system relative to true negative consideration, right? False positive to conditioned negative characteristics. We'll say I'm pushing into a bad camp if I'm having more elements being placed within the false positive consideration relative to the true condition negative characteristics, right? True condition negative takes into consideration all of the negative outcomes, like relative to negative outcomes. That's the summation of negative across that axis. Sensitive score, a sensitive system will have what? What is a sensitive system? That's one that is always going to detect the true positives, right? That's the one we want. We want it to be, it's sensitive if it doesn't drop true positives. Now, why do we think about something as, why do we understand that terminology? We understand it to be sensitive. If you're a sensitive person, right? You feel everything. You're very in tune with the environment. This means the model will push, if it has to, a discriminant boundary into sort of the enemy camp in order to make sure that it keeps all of the true positives, right? It will take maximization of true positive score as a sensitive model. It'll take maximization of true positives. It will start to have false positives. It will pull negatives into the positive camp in order to compensate for the possible loss that's characterized there. This is cases relative to overlap, right? So if we have positive cases, and then we've got some positive cases that are wandering out of the system, we typically might say, well, let's go ahead and put the boundary here so we maximize the performance of the model. The model says, nah, I don't like that because I'm very sensitive, okay? Hurts my feelings whenever positives aren't in my correct line. So I'm gonna go ahead and say, everybody's in the positive camp, okay? It's sensitive. It's sensitive, it feels things deeply, okay? You can't lose any of your friends. So in order to make everybody here, it has to make 3 new friends, okay? What are these? These are errors. This is saying that I will err on the side of caution, yes?
On the sensitivity part, do we have to put in the code for it to move that line or include the false positives, or does it do it itself?
We can penalize it.
Okay.
We can penalize it. The reason why a model might become more sensitive might be why. If I have 4 scores up there that I can penalize. Matter of fact, I have those 4, and then each of these 3, 4. I have 12 scores, 12 ratios that I can relatively penalize in different ways. Either the calculative ratios or the core values that are generated of those ratios. So if I say here that a positive class as a negative, right? So a positive class negative, right? What does that end up being? That's a false negative, right? Fn. So an Fn is actually going to be more costly, right? So I'm going to calculate, or I'm going to multiply Fn by 1.2. Whereas I leave everybody else at 1.0. Okay, what's that going to end up doing? If I do this relative to error score metrics, and I'm counting up numbers, I'm going to say 1, 2, 3, right, for errors in the false positive camp, right? So these are now FPs. These are FNs, right? FPs are going to count as 1s, FNs are going to count as 1.2s. So this already goes to 2.4, right? This is 3, this is 2.4. It's catching up with the more numerous class in terms of its cost, all right? We call this a penalty assumption. So we can establish different penalties by scaling the relevant cost of a specific class of error. In this case, we'd say false negative scoring, right? So false negative type 2 error. We'd say a type 2 error penalty will induce increased sensitivity in the model. It won't do it otherwise, it won't do it on its own, right? I say I make a sensitive model. I make the model sensitive. Otherwise, it's neutral. It's going to attempt to maximize based upon, actually, it's typically going to attempt to maximize based upon what? Just the diagonal of the system. Usually the false scores are, an argument can be made that the false scores are a consequence mostly of that irreducible error characteristic of the system. They're mostly a result of noise, right? So the mixing or the blending of these two classes of material, these two cases, is consequence of they were originally supposed to be up here, right? But they were pushed over by some sort of noising. Some random injection of energy into the system caused me to recognize them in a different location, right? So there's either a metric error or an associative error or just a spread, a variance within the system. So we say that the misclassifications of the system are often due to variance characteristics. We'll do this, right? Push its boundary into the negative camp in order to try to keep all the positive score. A specific model will be penalized against detection of false negative considerations, right? Or pushing toward false negative considerations. So I can penalize Fn relative to true negative score by establishing this value. What does this look like? This says the difference between two things that are similar, co-associated, can be preferenced or can be pushed into a distinction by penalizing the model from getting into this specificity ratio. Let me go to another one, right? So medical tests are often utilized to explain classification because I think they work well. We already understand them to a certain degree. What we might look at here is the detection of COVID-19, right? So COVID tests are a great example. Before that, we could have done flu testing, right? Because you can talk about strains of flu. Now we all have our COVID understanding, so we can recognize what some of the issues are. COVID tests in the early cases, or early phases, utilized these distributed assays, right? They utilized some microcell assays where they would have bunches of different sensitive chemicals that would sort of change their operability based upon the presence of certain proteins within the sample. What happened was the original systems weren't very sensitive, meaning that it took a lot of the sample to actually cause the test to go positive. So what they started doing was they started doing chain reactions. The polymerase chain reaction is similar to the same mechanism they used to replicate DNA material, right? So they used a type of forward chain reaction to replicate the material of the virus or of the sample, and by doing so, they artificially inflated the percentage or the amount of those chemicals in the system. That would make the system more sensitive, right? So previously, they were only detecting about 80% of the cases. 80% detection means that's their true positive rate. That's when somebody actually had it and the test said they had it. Secondary characteristic here is we want to make the score more sensitive. That means we have to detect, or we're going to detect, a certain number of people who do not have the disease as having it. Why is that better in the case of the COVID? Well, because of the fact that you would prefer to have individuals who are actually negative test as positive, self-isolate for a few days, right? Take a vacation, and then, not infect other people in the process. That's potential characterization of it. The alternative perspective here is what happens with regard to the specificity of the system. If it is very important to know specifically whether or not you have the disease for the purposes of an intervention, right? Do I write you a script for some kind of medication, right? They now have antivirals that you can take if you get COVID. If you get a positive test early enough, they'll give you this medication, and it can be effective if you take it early enough. Similar to there is another one called Flovin that works for influenza. What happens if you have influenza and the test is really, really sensitive? Well, COVID and influenza have a lot of similarity in terms of their external mechanical structures. So if I make the model really sensitive, I'm pushing over from the COVID camp into various adjacent flu viruses, okay? So now I'm capturing all the COVID, yes, but I'm also capturing adjacent flu viruses. Now I'm prescribing medication that's intended for COVID to populations that actually have influenza that are probably not going to get any positivity out of the medication. It might create toxicity, it might create feedback. It also might reduce the sensitivity of that medication in the future with regard to various circumstances. So a sensitive test is one that can tell the difference between COVID and the flu, right? It's one that can distinguish between similar items, whereas a sensitive test is going to be the one that can detect them even at low concentrations or small quantities, right? It's very sensitive, and it will go out and expand its region in order to be able to find stuff on the periphery so that it doesn't forget. It will err on the false positive camp in order to maximize the true positive camp. What's your question?
So you say that the influenza and the COVID has the same structure of the proteins or whatever we think about it, right?
Sure.
So if those are if those are really close to each other, then they have the same sensitivity, right? So if we model those to each other,
Yeah.
then are we getting the false positive, like those two are the same, but we cannot treat people because some of them patient may be if I test for COVID, some of the patient will come for the influenza. I'm confused about that one.
You're perfect. You're perfect. You know why? I want you guys to think a second. What was one of the dilemmas that we came across that mirrors this? Well, we wanted it to be specific, accurate, but we want it to be robust against changes between data set typing. Welcome back to the bias variance dilemma. I told you to visit again. This is irresolvable, okay? You can only balance it.
Okay.
It will not be fixed. You cannot find the perfect value. The best you can do is make the best out of the bad situation, because all the data is going to overlap across certain dimensions of the characteristics of something. Let's say a protein. You have different concentrations of the protein or slightly different shapes of the protein. We can take those and we can project them as a feature. We can see their relative densities. But what did we see with respect to the linear discriminant analysis projection? We noted that the densities of those two clusters overlapped one another fairly heavily. So how do I untangle those? I do my best with the LDA projection. I do my best to minimize the score metric error that I'm being provided with here, not simply just by inclusion or exclusion of singular samples, but by balancing class memberships relative to what are the most costly for the task that I'm assigning it. This is the reason why creating machine learning models is almost as much art as it is science with respect to the fact that you can't apply the same overarching logic to all solutions in all spaces. Medical requires you to think about and know and understand the implications and the impact from cost, individual cost, value analysis perspectives in order to be able to know what features, what penalties to apply during the training process such that the model will balance at the appropriate place, the appropriate point within the system that we designate as our ideal value proposition balance. Usually this is data-driven, very data-driven, right? So based upon the samples we have, we select those balanced values in order to try to optimize the output scores that are provided here. Any of these output scores can be sort of tacked on to the end of an error metric. As we've talked about previously, we can say error or the association of the system plus some incorporated error as a result of a specific score type relative to the ratio of the number of samples in the positive or negative count in that case. Did you have a question or did I resolve?
Yeah, so, do we quantify these differently for each model then?
Yeah, I mean, they
Okay.
are absolutely 100%.
And then
Yeah.
what variables are associated with like each one when you're like looking at your model
That is,
or is there a
the
special calculation?
quality of a predictor relative to its capacity to predict positive or negative outcomes, right, is going to be based upon the coefficients of the regression of the model or replacement of the positions, right? So we can say that the coefficient of the linear discriminant algorithm is related to the angle, the rotation of the space we're projecting on.
Right.
So that maximization of that coefficient of all the samples in those spaces, all I can then do is attempt to try to bias the discriminant surfaces. I can make the surfaces and I can place them at their midpoints, right? But in order to try to take in a slightly higher or more sensitive score, I push the discriminant boundary over a certain amount. How far over? It's weighted based upon how many positives are in the negative camp, right? How far do I have to go in order to make sure I get them?
Right.
right? So I'm gonna keep going over until I make sure that I'm capturing all the relevant value from the system. And as I said, I can penalize the system to do that, iteratively increasing the values until the scores start to balance in the way that I like them. But I have to understand that every time that I increase or every time I decrease my true positive score, true negative score, by a ratio of the number of now false negatives that I'm taking in order to maximize true positives. It's all connected, okay? It's like the meme where the guy's up there and there's the board behind him. It's like, it's all connected, you know? Draw the lines between them. The characteristic is, in order to get these guys, I have to sacrifice these guys as I move the discriminant boundary over that direction. So the ratio of true negative score, right, relative to false negative score is going to drop in order to maximize true positive score relative to false positive score. Right, so these now become false positives, but they came out of true negatives. So true negative goes down in order to optimize true positive. So you're going to see everything changes. The total number up there in that matrix is the total number of samples. Right, so that total number is just going to get redistributed. It gets sorted into its various camps. Okay, we spent a lot of time on that, but I'm fine with it because I think we talked through stuff. I got some questions on this, but I wanted to make sure we're done with 4 today. But confusion matrices often return class characteristics such as these. Notice, where is the predicted label class? Predicted label's on the bottom now. You can just put it wherever you want, okay? It's arbitrary. But it's always going to be a reflection of predicted versus true somewhere. Predicted is going to be on one axis and it's going to be orthogonal the other. Somewhere, right? Well, they always have to be, you know, at a 90-degree angle to one another. So we say case, this is positive, control is going to be the negative consideration, case and control, right? So case to case, true positive score, upper right-hand corner now. So I kind of did this on purpose, right? Positive, predicted, label, true label, predicted, right? Or no, excuse me, I flipped it around. You're right, it's bottom right. Case, case, I thought that one was case. Case, case, bottom right. Sorry. I didn't mean it. Thank you for the quizzical look on your face. I was reading wrong. That's the reason why they're called confusion matrices. Confusion from people. We're going to use a metric that we call the receiver operating characteristic. Anybody ever seen this before? Ever heard of it? Okay. The reason why it's called receiver operating characteristic or ROC is because they used to use this for detection of radar signals for classification of specific types of aircraft for military use purposes. The area under the curve, or AUC, is related to the confidence of the identification of that specific pattern or that specific template as being positive or being enemy aircraft positive, or even a specific type of aircraft positive, relative to this score ratio, right? We have the true positive rate, TPR, over false positive rate, FPR. So the greater that the relative score for true positive goes, right? That is relative to how sensitive the model is, how well we detect the target. We're going to have a certain amount of false positive that's created as a result of moving the boundary over. As I move the boundary over, the true positive score increases, right? But likewise, if there's a heavy overlap between the two classes, the false positive rate also increases. So what we see here is the curvature is indicated as the location where we are going to maximize relative true positive rate at the cost of false positives. So this is how many false positives are being created as an attempt to try to increase the true positive detection rate. This is to capture the values that we're looking for, the values we're intent on. We're making the boundaries lax on the classifier space. And by making the laxity, the fuzziness of those boundaries, we're going to be including more false scores within the positive scores, right? So false positives are going to increase as a result of trying to maximize true positives. This is the balance. This is the graph that shows the bias variance dilemma in an alternate dimension with regard to classification, right? If I want to maximize true positive rate, I must be satisfied with or understand that there is going to be a minimum false positive rate that will be associated with it. At 80% true positive rate, I will have something like a 40-ish percent. So let's say 85% or close to 90% true positive rate. I'm going to have about a 40% false positive rate. All right? This curvature explains or shows the entire sweep of how true positive rate changes, or I guess you'd say of how false positive changes. Technically, it's false positives change relative to true positives inclusion. So as true positives arms get wider, right, it's accepting more and more false samples into the positive class. So what happens in this case is it's actually the upper section of the graph is the maximum performance of the classifier relative to each of those ratios. So as the boundary is being moved over, as the boundary changes, we see the curvature created by that change in boundary. And we say that the quality of the classifier, the quality of the ability of a classifier to be imposed for detection sensitivity versus specificity ratio is expressed by the area underneath the curve, or AUC, as an integral of this region down here, okay? This whole region underneath here. So this means this area is exclusionary, right? You can't get to it because of the fact that a good chunk of this error is a result of internal variance within the data itself. Now, what happens if it's totally 45-degree angle? That's a classifier that does absolutely nothing. All right? This is your coin flip classifier. Why is it coin flip classifier? Because it's saying that every time I attempt to increase the true positive rate, I end up with an equivalent false positive rate. Okay? So every time I try to move the boundary around, I flip the coin about which side of the boundary it's on. This is probably, if you get a perfect 45-degree ROC curve, you've done something wrong in your calculations. Like there's not something wrong with the model. It's miscalculated. The reason why is because if you created a perfect 45-degree ROC, okay, you've created something amazing. Because there are no perfect random number generators, okay? That would essentially be a perfect random number generator because it would be the exact boundary between where two things are likely to land. The other consideration I've seen beforehand, and this happens occasionally when people start messing around with rocks, especially in R, because the coefficients flip. If you have a negative ROC curve, your model isn't messed up again, okay? It's not messed up. Just the way you're plotting the ROC curve is messed up. You flipped the scores. There is no such thing as a negative ROC curve. It can't happen, right? Because you can't have additional changes of negativity in the positive case solution. So if it goes negative, you're just plotting it wrong. So flip the scores around because honestly, if it were the case that it was flip scores, it's still just as good at detecting in the opposite direction. So then you just turn all the negatives, ones into zeros and zeros into ones. Okay, you flipped the scores of what is a positive and what's a negative. That's the only thing that can happen. Right? I was taught that. It helped ease a lot of stress in my life. You know, whenever I saw things that were like, "What's going on?" and it's like, "Oh, I just flipped which was case and which was control." Okay, good.
Yeah, I understood.
Okay. We also look at this. This is a cool plot if you're interested in getting a little bit more information. This one has a nice little understanding of the planar characteristics relative to two density outputs. So we see here that we should have probably included or placed the discriminant boundary along the region of the median between the two classes, right, where they're equivalent or they were equal with respect to likelihood. However, we've pushed it over in order to attempt to capture more information. we established a threshold that says we want to have at least something like 90% operator characteristic or 95% operator characteristic. And at that threshold, we're missing or must have tolerance of a 43% false positive rate. So from a score perspective, we know here, this was 92. I was eyeballing it from the graph here. It's 92% true positive rate, right? Sacrifices something relative to a threshold of about 0.43 or 43% FP integration. So this is going to be an increase in false positives as a result of that characteristic. Notice here, though, that the false pulse rate does not actually equal the value of the RFC integration. This can happen, okay? Because it is a data-driven conclusion. It's one that's based upon likelihood estimates. When I shift over those regions, sometimes it doesn't have that exact output value in these cases. But what the argument here is, the threshold of the system, I can't go past 43. I don't want to go past 43% increased prevalence. What I was able to do is I was able to get up to 92% while hitting only 38% relative error, right? So many times, if you go past that, it may have a very, very quick increase. It may stair step up very quickly in terms of its false positive scoring. So whatever false pulse is used as the positive case in this particular demonstration. But this is a good relationship between understanding of ground truth, right? Ground truth is no pulse versus pulse. And then we have cases where we're detecting certain characteristics. We say no pulse is true in this case, but we had individuals or characteristics within the system that exhibited pulse readings, but were actually non-pulse readings. Now, why would we want to try to be able to always detect pulse? Because always detecting pulse is better, right? We want to get as many of the pulses as recognized. What might happen here? What's the median of pulse, for instance, as a reflection of frequency rate? What's the average pulse? Somewhere around the neighborhood of about 70 to 75 BPM, okay? We note that some people can have pulse that goes past, well below the median value of that score, right? So they can be people such as professional sports players can have pulse rates in the 40s due to really, really high physical fitness, okay? Their hearts are so strong that they don't need to beat as frequently because they have such higher ejection fractions. So guess what? We may actually miss somebody that's in incredibly good shape whenever we're running a pulse meter on them because their pulse rate is so low. However, what we want to do is we want to be able to distinguish. We want to be able to tell the difference between whether or not somebody has a pulse and somebody doesn't have a pulse. Because what don't we want to do? We don't want to hit them with paddles, right? If they've still got a pulse, because that's going to go the opposite direction. What's that going to do? That's going to take the pulse away, right?
I'd start fighting.
It just bit inverts, whatever it is, okay? The paddles are a bit inversion again, right? So if you do have a pulse, you're a 1. If I hit you with paddles now, it's a 0.
That's why I'd start fighting you.
That's almost guaranteed. Okay, that's almost guaranteed. The other direction, if it's at a 0 and I hit you with the paddles, it's not guaranteed to go back to a 1, okay? Clear again, clear is still not a 1, okay? What happens if you do get a pulse, you hit them with the paddles, there was a pulse, and then it was below the threshold of integration? That's a missed pulse, right?
Missed pulse.
Low frequency pulse. So we want to make sure that we're erring on the side of caution of detecting even little spasms, that are happening with the heart, okay? I don't know why, but I'm making some ridiculous 3 days today. Hopefully it'll be memorable. So this is the best that I think I can do with regard to a singular visualization that shows something that you can relate to and understand, get the core readings out of. Yes?
And where, on
This
the
is the
bottom
end
part,
of, oh yeah, go ahead.
on the bottom part, where the dot is what the confusion matrix is part of, correct?
Correct, and if you look here, it says threshold is 0.43, but look, 0.4 is right here. So what does it mean by threshold 0.43? Right, that's establishing where the likelihood core metric is here, for the output for the probability metric.
Oh.
What happens if we put it at exactly 0.5? That's not always going to be the maximum AUC score for the underlying system. What it's saying is that if I push the threshold down to 0.43, for the likelihood ratio, expanding the pulse camp into the non-pulse camp, I have pushed over that linear discriminant. I've pushed delta over by 0.07 in order to try to maximize this score right here. Make sure that we detect all pulse rates. I'm gonna have 4, I'm gonna have 38 here, and where that's coming from is right here, right? It's coming from the percentage or probability relative to false pulse rate being detected as a result of adjusting from where it should have been at 0.5 here over to 0.43 for the adjustment of that threshold. This threshold indicator probably should be up there or should point up there. I might put a little line in it and re-update it. That was what I was trying to describe earlier, is that by establishing the threshold for the probability of the first likelihood case class is not going to have an equivalent ratio of relative case inclusion in the confusion matrix. So just because I put it with respect to the medium likelihood does not mean this automatically shifts to 50%. Why would that be the case? Once again, these are derivative ratios. They are what's called generative. So we generated the functional understanding of the distribution function, right? The characteristics of this smooth continuous curvature from discrete values. So the discrete values have known quantifications and known positions. They don't necessarily have to fill in the distributions uniformly in order to be represented, because we're making an assumption about that surface being Gaussian or normally distributed. So I technically could have a bunch of samples over here that really fit my core normal, and then I could have very sparse sampling over here that I'm inferring to have normal ratios within that system. So just because of the fact that I place it on the 50% line does not mean that half of the samples are going to be in the non-class camp. That's a consideration. So you won't get perfect exchanges in that way. Okay. That's the end of the supplemental slides. I'm going to make sure that we don't have anything on the external slides that we need. Just real quick for you guys, 1 second. Okay, we did not look at Fisher. I will look at Fisher with you later on. The rest of this is actually just the descriptions, the same things that we were talking about with regard to ACs. So we'll talk about these for the calculation stuff at the beginning of Wednesday, and then we will probably skip the section at the end we have to skip because it's based upon logistics. So quadratic. So we're not going to do quadratic discriminant. You guys do quadratic discriminant in your other material. So we'll quick skip quadratic, and then we'll talk about naive Bayes really quick on Wednesday, or as quick as I decide to talk about it. We may only get through half of 5, before we get to our exam. When we get there, and we'll do just what we have. But my goal would be to try to be as much through 5 as we can. We do technically have like 4 more classes before I have a schedule for the exam, but I believe I may have to do Friday's lecture as a Panopto supplement. I've been asked to give a lecture in a new class that's going to be a bioinstrumentation introductory course over there on Friday, the 4th. So I'll be doing that at 10 o'clock. Yes.
I would not be mad. That would save me some gas.
Okay, well, I'll make sure to let you guys know in advance. If I do, I will record the lecture for here in advance, upload for that for you guys so we don't miss the lecture, but I will likely be over there giving that. And I may make that available to you guys as well, because it's going to be related to, it's going to have some implementation level stuff with regard to EEG, electroencephalography, brain data. So I'll try to see if I can get that recorded. Have that for you guys as well. So, see you guys on Wednesday. We'll talk about Friday as it comes up. I believe it'll probably will be recognized as solid. We're going to be skipping that and making it online. Yeah.
And we're looking at a test a week from this Friday.
Correct.
Okay.
Yeah.
Speaking of
All right. Thank you.
that what I get fixes on it, it can help you on the screen.
Awesome, thank you.
I've sent it you, John. I've sent you the file in Gmail.
Oh, okay.
My thesis.
If you didn't sign in, come on in and sign in. trying to encourage more attendance, and I want to have people here as soon as we can, whenever we're starting during the day. I know I'm not always perfectly on time, 5 minutes is not a big deal, but 15 or 20 starts eating into your class time. Distracting too, so. Originally, I wasn't gonna let you guys sign in, but most of you are here within a reasonable period of time, so I wanna make sure you guys understand